So far, all of the data that we have been working with has either been stored in the static data area or in the stack. Static data area items include string literals or local static variables like we used for our random number generation function, or global variables which are visible throughout the program. Things on the stack include parameters for functions and also local automatic variables within functions. Now we're going to take a look at the area of memory called the heap, in which you can dynamically allocate objects, and these objects can persist regardless of which functions are currently being called or returning throughout the execution of the program. Individual objects can be allocated with new, and then later on deallocated with delete. Arrays of objects can be allocated with the new and the square brackets, and later deallocated with the delete and square brackets. Now the downside of dynamic memory is if you keep allocating things with new and never get around to deleting anything, you can create for yourself what's called a memory leak, which can eventually cause your program to slow down and eventually crash. Languages like Java and Python don't suffer from this because they are what are called garbage collected languages, and they detect when an object no longer has any references to it and will automatically clean up that memory. Now the downside of garbage collection, on the other hand, is that it's slower than if you as the programmer take control of deleting objects when you no longer need them. So there are pluses and minuses to each approach. Container objects, lists, stacks, queues, trees, general graphs, sets, heaps, these are the kinds of things that grow and shrink and change size while the program is running, and it's for these kinds of things that we very often use dynamic memory allocation. We're going to get into lists and trees and heaps and stacks and queues in upcoming lectures. Okay, so if you want to allocate a new object of some particular type, you first need to have a variable declared as a pointer to that type of object. Then you use the keyword new followed by the data type of the thing you want to create, and if memory is available, that causes enough memory for that type of object to be allocated in the heap. And what you get back from new is the address of that newly allocated object. Now, if you lose track of that pointer, you have created for yourself a memory leak. To eliminate that object that you no longer need from the heap, you should use the delete operator on the pointer that's pointing to that object. Now, that doesn't literally delete the pointer itself, but it does end up deleting or deallocating the object to which the pointer is pointing. If you allocate with new one of the fundamental type objects, such as an int or a char or a double, and you don't specify any initialization value, then storage is allocated, but the storage contents is undefined. This is just like if you have a local automatic variable in a function that you haven't specified an initial value for. You can specify initial values if you want in the usual ways. And here on slide 5, we have an example of a program that's allocating 3 int objects on the heap. The first is uninitialized. All right, so the first new int that's being allocated here is uninitialized. So an int's worth of memory does get allocated in the heap, and the address of that object becomes the initial value of the pointer p1, but the contents of that int object are undefined. In the next new statement, we're allocating an int that's initialized with 3, and the address of that allocated object goes into p2. And then in the third case, we're allocating an int containing a 7, and the address of that goes into p3. We can now interact with those int objects indirectly through these pointers by using the star contents at or indirection operator. And eventually, when we're done using this dynamic memory, we should use delete on each of those 3 pointers. And that will cause first the int that P3 is pointing to be deallocated, then the int that P2 is pointing to, and finally the int that P1 is pointing to. Okay, now as it happens, all of the memory allocated in the heap is deallocated automatically when the program ends, that is, when the main function returns. But you should never just take that for granted. You should always take control and make sure that you are deleting objects that you have allocated with new. Now, for fundamental type objects, you can request the default value as the initial value for those things, but just using an empty parenthesis or an empty set of curly braces. And it turns out that the default value for all of the fundamental types is 0. Whether that's a char, okay, so for a char that would be the null character, or a bool, which would be false, or an int, or a double, or all the various other, long int, long double, and so on. Here on slide 7 is an example of that kind of notation. We're allocating a new int, but we want the default initialization value for that int, so that's going to be 0. Consequently, P1 is going to be initialized with the address of this newly allocated int on the heap containing a 0. And here is the same idea, just using curly braces instead of the parentheses. So P2 is initialized with the address of a newly allocated int containing 0. Okay. Now, there's another place where we use parentheses, and so you might get confused into thinking, well, if I can allocate a new int with a default value by using parentheses after int, can't I just get I declared as an int with an initial default value? Unfortunately, this notation means something entirely different. This notation is a function declaration, saying that I is a function that takes no arguments and that returns an int. So for local automatic variables, you would have to either put a 0 inside the parentheses or use the equal sign instead of the parentheses, or put a 0 inside the curly braces. You can't get away with just saying open and close parenthesis in that case. Okay, so those were examples of allocating and later deleting individual objects. If you need an array of objects, there's a small modification that you make for new. You say that you want a new, and then you give the data type, and in square brackets specify the number of elements in the array of that type that you would like. What you get back then is the address of the first element in that array, and that becomes the initial value of your pointer variable that you're using to keep track of that dynamically allocated storage. Now, one bit of awkwardness that people often get wrong when they allocate an array of objects in this way is you have to use delete with square brackets in order to deallocate the array. If you forget the square brackets and the elements in the array are some higher level class type that have so-called destructors associated with them, then the forgotten square brackets will cause those destructors not to be called. That's jumping the gun a bit. We don't know about classes or destructors yet. I'm simply just pointing out that if you use square brackets to allocate an array of objects, you'd better also remember to use delete with square brackets to deallocate that array. Okay, so if you allocate an array of the fundamental type objects, an array of char, an array of int, an array of double, and you don't specify any initialization, then you'll get an array whose elements are all undefined. But you can use empty parentheses or empty curly braces to indicate that you want the default initial value, which is 0. And if you have a compiler that's compliant with C++ 11, which by now virtually all compilers are, in curly braces you can actually specify a whole list of initial values that you want for those elements of that dynamically allocated array. All right, so here on slide 10, we have an example program, and here is the diagram of what's going on in memory when we run this little example program. So I'm allocating a new integer array with 3 elements, and I have not initialized that. So an array of 3 ints is going to be allocated in the heap. The contents are not going to be initialized. I'm going to get the address of the first element of that array back, and that will be the initial value of P1. Okay, so P1 is a local variable in main, and it is initialized with the address of the first int, the sub-0 int, of this array of 3 ints. But we don't know anything about the values of those ints. In P2 and P3, on the other hand, we have addresses of the first elements of a couple of arrays that are initialized to defaults, that is, to zeros. Okay, so we allocate a new integer array of 4 default values that P2 is pointing to, and an integer array of 2 default values that P3 is pointing to. Okay, so P2 is pointing at the initial element of an array of 4. P3 is pointing at the initial element of an array of 2 default values. And here, if you do have a C++11 compiler or later, illustrates the idea of an initialization list for the array. So this array is initialized with 3, 9, and -4. I get the address of the initial element back, and that becomes the initial value of main's variable P4. Now, we have a couple of for loops displaying the arrays that P1 and P2 point to, and below that we have a couple more for loops displaying P3 and P4. And then, of course, we have to remember to delete these arrays when we no longer need them. Since you allocated them with the square brackets, you have to remember to delete them using the square brackets as well. Okay, null pointer is a special token introduced with C++11 that means a pointer that does not point at anything. Prior to the introduction of null pointer, and even since the introduction of null pointer, 0 is used to mean exactly the same thing. Now, it turns out that if you ask new to allocate an object or an array of objects, and there is not enough memory available for new to do that, by default, what new does is to throw something called a bad alloc exception. Thrown exceptions in C++ are like raised exceptions in Python. And generally, if an exception gets thrown in C++, the program immediately dies. We'll get to more details of how to handle exceptions a little bit later on in this course. Now, if you don't know how to handle exceptions, and you fear that requesting memory might fail, one way to avoid the exception is to include this no-throw parameter between the word new and the data type that you're trying to allocate. In this instance, instead of throwing an exception if it can't allocate memory, new will return a null pointer value instead. And then you can just use an ordinary if decision to see whether null pointer was returned and try to do something to clean up the mess if memory was unable to be allocated. Okay, well, slides 14 and 15 here contain a lot of detailed warnings that I'm not going to read to you in detail. Basically, the heap is an intricate and delicate data structure that unfortunately is easy to corrupt. If you allocate something that you forget to delete, you get a memory leak. If you allocate something and delete it twice, that can lead to corruption. If you delete something that never was allocated, that can lead to corruption. If you allocate an array of things, but you don't delete it as though it were an array, that can lead to corruption. There are all kinds of problems that can arise. So the bottom line is, dynamic allocation is both powerful and dangerous. Application developers, who on average are somewhat lesser skilled programmers, although still probably pretty highly skilled, usually stay away from dynamic memory allocation. Dynamic memory allocation is best to isolate within libraries that are intended for other people to use, where they can be rigorously tested and maintained by programmers who tend to have more expertise than application developers do. All right, so we're going to use a lot of dynamic allocation in linked lists and trees and other dynamic data structures coming up.